Okay, woohoo! Our final quiz! We made it! And let's have some fun. 10 problems, and I think there'll be a couple of them that are going to be extra fun. All right, we'll start, and here we go. Number 1. Let h of x be a function such that the integral from 0 to 2 of h of x is 1, the integral from 0 to 3 of h of x is 2, the integral 0 to 4 of h of x is 6, integral 1 to 5 of h of x is 5, integral of 2 to 5 of h of x is 7, and find the integral from 1 to 3 of h of x. So we don't know what h of x is, and so we're never going to find it out because we just don't have enough information. But notice the problem doesn't say what is h of x. The problem is about the integral from 1 to 3 of h of x. Now, one thing that might be helpful to think about what's going on here is we can draw ourselves a number line. And let's sort of figure out what we know. So we do know that if we go, let's see, where do our numbers go? They go from 0 up to, it looks like 5. So I'm just going to mark 0, 1, 2, 3, 4, 5. I don't know why I gave myself so much space there. All right. We know if we go from 0 up to 2, what that is. That's equal to 1. We know if we go from 0 up to 3, that becomes 2. If we were to go from 0 up to 4, well, that's worth 6. 1 up to 5, well, that would be worth 5. And 2 up to 5, well, that's worth 7. So that's what we know. Now, the question is, what are we after? Well, we're after from 1 up to 3. So that's our unknown. Now, in some sense, we can kind of get a notion of what we need. You see, because there are certain things that we have to be using. So, for instance, notice we want to start at 1 and we want to end at 3. Well, if we're going to start at 1, we've got to use, the only other place where 1 shows up is in this piece of information here. The only place where 3 shows up is in that piece of information there. And, okay, well, the question is, how do we fit things together? Well, interesting problem, right? Interesting problem. But here's the idea. It's like, okay, I know I need to start at 1, but if I use this one, I have to somehow account for 5. And we say, oh, wait a second, there's something else that starts at 5, so we can use that information. Well, that says that gets us to 2. What else starts at 2? Well, that starts at 2, ends at 2. Okay, and now we might have our great aha. We have sort of things linking up. Now, this is sort of getting complicated and weird. Let me start this in a slightly different way. Our goal is to go 1 to 3. We see that for 1, we've got to use this integral. So 1 up to 5. So I'm using ones that I know. And I say, okay, now I want to say, look, the 1 is good, 5 not so much. So I say, well, what do I know about 5? Well, I have this integral, so I'm going to go 5 up to 2. Now you might say, wait a second, we have 2 to 5. Oh, there it is, 2 to 5, not 5 to 2. Well, that's okay. See, swapping the order does what? It really changes your sign. So that's all right. So we'll fix that in a second. Now we're at 2, okay? So what else uses 2? Well, the only thing that uses 2 is the 0 to 2. So I'm going to go 2 to 0. H of x dx. And, all right, well, now what? Now I'm at 0. Now there are several things that start at 0. 0 to 2, 0 to 3, 0 to 4. Well, I want 0 to 3. Now, what's going on here? If we think about what's going on, we say, remember one of our fun facts. So recall that the integral a to b of some function, I'll call it f of x, doesn't really matter, b to c of f of x, because these pieces, the bounds match, what we can do is put it together and we get a single a to c f of x dx. So when the bounds match, we can stitch together. And of course, the insides have to match as well, but that's all right. Notice we've set it up so that the bounds all match. And therefore, the integral from 1 to 5 plus 5 to 2 plus 2 to 0 plus 0 to 3, this integral is the integral that we want. So this is equal to, I'll put it up here, the integral from 1 to 3 of h of x dx. Good, 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 good. Now, we're not done yet, because we have to say, okay, so what are these? Well, from 1 to 5, that would be, where's 1 to 5? There it is, it's 5. From 5 to 2 is the opposite sign of from 2 to 5. So minus 7. 2 to 0 is the opposite sign of 0 to 2. Minus 1. And 0 to 3, well, that's 2. So if we put all these things together, 5 minus 7 minus 1 and 2, it's actually pretty easy. The 5 and 2 make 7, minus 7 is 0. So we end up with minus 1. Now, you might say, cool, because that is the right answer, but you also might say, wait a second, when did we use this? And the answer is, we never used it. You see, it gave us a lot of information, but it didn't say all the information was needed, and this is a case where, lo and behold, there are some things we don't need to use. This actually happens quite a lot out in the real world, right? You're going to get a lot of information. It doesn't mean that every piece of information is valuable. So don't panic too much if you're not using everything. But you should definitely think of, if you get stuck, what aren't you using? But okay, so that's number 1. It's kind of like a puzzle. How do you fit the pieces together to get what you want? Number 2. So here, it's a different kind of puzzle. See, because our bounds are all the same. So we're told that the integral from negative 7 to 8 of 4 f of x plus g of x is 10. Negative 7 to 8, the integral of that, of 2 f of x plus 3 g of x is 0. And we're asked to find, well, what's the integral of 5 f of x minus 3 g of x? So what are we testing here? In some sense, again, we don't know what the functions are, so it's not about finding antiderivatives. This is really saying, do we understand how integrals work? So, all right, we do understand a little bit about how integrals work. You see the plus? It's about addition. And integrals work like addition. So you can break up integrals over addition, and also the constants you can pull out. So what we can say is that the first statement, if I pull out the constants and break it up into pieces, I have 4 times the integral from negative 7 to 8 of f of x dx, plus the integral from negative 7 to 8 of g of x dx, and that would give me 10. And I'll do the same thing here. 2 integral negative 7 to 8 of f of x plus 3 integral negative 7 to 8 of g of x would produce 0. Now, here's sort of our great moment. You see, if you stare at this, and you don't have to stare very long, you say, wait a second, this expression, integral of negative 7 to 8 of f of x dx, it's a number. When you're doing a definite integral, and the bounds tell us it's a definite integral, this is some number. And by the same idea, integral from negative 7 to 8 of g of x dx, it's also a number. So what I have is I have some combinations of numbers. So let's call the first number, I'll call it capital F. So it says 4 capital F plus capital G because I'll call it this, wherever that number is, capital G equals 10. And here, I'll say, this says 2 capital F plus 3 times capital G equals 0. All right, so what I can do is I can solve for capital F and capital G. For instance, if I multiply the second equation by -2 and combine, this will be 4 minus 4, which would be 0F. G minus 2 times 3 is minus 6G, so minus 5G equals 10 minus 2 times 0, which is 10. Or, if I divide both sides by -5, G is -2. Now I know what G is, I can plug it back in, and I can say, for instance, now 4 times F minus 2 equals 10, or 4F equals 12, or F equals 3. All right, well that's great. So what we have is that we now know what these pieces are. The first integral is equal to 3, and the second integral is -2. Well, why does that help us? Well, what are we after? Well, what we're after is we can break that up. 5 integral -7 to 8 f of x dx minus 3 integral -7 to 8 g of x dx. Well, that would be 5 times 3 minus 3 times -2. Well, that's 15, and these two negatives make it a positive, so that'll be 6, and 15 plus 6 is 21. And that's the answer, 21. So this is sort of testing our idea of breaking things up over addition, and therefore being able to solve. And of course, our favorite thing, 2 equations, 2 unknowns. And what can you do? What can you do? All right, that's number 2. Number 3, find the integral from 1 up to root 2 of the square root of 2 minus y squared dy. Now, one of the things that you oftentimes get into the habit of doing is saying, integration means find an antiderivative. Can you find an antiderivative of the square root of 2 minus y squared? The answer is, if you take Calc 2, yes you can. But this isn't Calc 2, this is Calc 1. Okay, so maybe we can't find an antiderivative. Does that mean we can't answer the question? Well, no, it just means we don't have that tool, but maybe there's another tool. And a lot of the motivation for calculus comes from geometry. So let's think about what the geometry is saying. So I'm going to think of this as a function here. So let's suppose I think of this, I'll just come up with a symbol. Let's suppose we say z equals the square root of 2 minus y squared. So if I hear y and z, what does this look like? Do you recognize what that would be? Z equals square root of 2 minus y squared. It's not so clear right away, but if you get rid of the square roots, because I think square roots oftentimes throw us off. Z squared equals 2 minus y squared, or we could say y squared plus z squared equals 2. That we do know. That's a circle of radius. Oh, what's the radius? Be careful. Is it 2? No. See, that's the radius squared. So radius root 2. Now that's what z squared plus y squared equals 2 looks like. But when we see the square root, what happens is we don't take the whole circle, we take the top half of the circle. So here is root 2, and plus we're not going to go take all the circle, we're going to start at 1. So let's say this is where 1 is. 1 is smaller than square root of 2. So now we can say, if I look at this integral, I can interpret it geometrically. Because one of the powers of integration comes when you're able to say, this integral represents something, And I'm going to use that knowledge of what it represents to get a better understanding of what's going on. So here we go. There's our shape that's being represented. So we could say we can solve this problem of what this integral is if we can find this area. So the area here, so the area of this shape is equal to the integral from 1 to root 2 of the square root of 2 minus y squared. All right, so we've transformed our problem into a geometric one. What's the area of this particular shape? Now the problem is it's not the whole circle. Now there's a couple of ways we can overcome this, and there's actually some kind of fun ways. Now this point up here, it's not just any random point. The x-coordinate, or sorry, I guess the y-coordinate is 1. What's the other coordinate? 1 comma. Can you see what goes there? Well, if you plug in 1, you'll get square root of 2 minus 1, which is 1. So it's almost like you're halfway there. Now, there's a couple of ways we can proceed. I'll show you kind of a fun way. I think this is really cute and adorable. And I love cute, adorable things. Imagine that I were to take this and flip it over. Whoop. These two pieces, other than the fact that I'm a bad artist, are actually the same. So it's like, ah, that's cool, that's cool. Now, why do I mention that? I'm after the area of this piece, and let's call this, we'll call this A. So let's think about what I can find. I have this thing I'm after, which I don't know, matches with this piece which I'm after, so I equally don't know that. How about, what else do I have? Well, I do have something I do know. Do you see it? It's right here. It's this square. How much area is in that square? Well, it's a 1 by 1. So this has area 1. Cool. Cool, 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 cool. Now, is there anything else I can find the area for? Well, I can think about the area of a quarter of a circle. Now that I can do. See, the problem was that the original part wasn't a nice piece of a circle, but a quarter of a circle I can do. So I can take the area of 1/4 a circle, subtract out the area of the square, and what I'll be left with, if I do that, I'll have the area of these two pieces, and then I can divide that by 2, and then I'm done. Because that will be the area of what I'm after. So, well, what's the area of 1/4 of the circle? Well, in general, the area, the 1/4 will be a fourth, and to find the area of a circle, it's pi r squared. Okay, so that's the area of 1/4 of the circle. The area of a square, well, that has area 1. We divide that by 2. Well, notice that this square root of 2 squared will be 2. If I divide it by 2, that still leaves me with these cancel. So I'll be left with a pi over 4 minus 1 over 2. And that's our answer. Pi over 4 minus 1 over 2. And the good news is that is a positive number. So, phew, good. We'd be nervous if you got a negative number, because we're interpreting this as an area. And if you have a negative area, well, that means we need to revisit our interpretation. But, all right. Are there other ways to do this? Yeah, but they all boil down to geometry. Now, another alternative you could have said is the following. You could have said, well, let's think of it as I take a wedge. So suppose I have a wedge here. Now notice that this wedge of the circle, how much of the circle is that? Well, if you were to go all the way around, how many wedges do you need? You need 8 wedges. So that area of that wedge is 1/8 the area of the total circle, which is pi root 2 squared. But now you say, okay, well, that's great, that's the wedge, but I want to take that part out. So, because I only want to be left with this piece over here. Well, now that's a triangle, 1/2 base height. And if you simplify that, that's pi over 4 minus a half. So again, that's a different way you could also see this. But it's really coming down to geometry. Can you see the geometry? And kind of a spoiler, you'll see probably multiple times by the end of today. If you see like a square root of a number minus something, oftentimes it's very helpful if we say, I wonder if that's a circle. And it will suspiciously often be a circle. It's a way for us to do integration without having to do antiderivatives. Number 4. Looking over attendance records, the calculus instructor has discovered as the term progressed that fewer students came to lecture, thus breaking their supersized heart. In addition, 2 weeks into the semester, there were 150 minus 20t plus t squared students per lecture. Find the average number of students per lecture through the 12th week, i.e. from time t equals 0 to t equals 12. Now, there's one key word in this problem that if we see it, pretty much gives away everything that's going to happen. And it's not heart, but it is true, calculus instructors have a lot of heart. Now, the key word here is average. So, average actually means something. And so once we understand what the key word is, that's going to tell us what the right formula to use will be. So, the average from time t equals a to time t equals b is given by the following. 1 over b minus a integral a to b of the value of the function f of t dt. So, now that we know that's our formula, we just got to work it through. So we know our a and our b. That's given here, 0 and 12. So, 1 over 12 minus 0, integral 0 to 12. And our function, that's 150 minus 20t plus t squared. All right. Well, let's make progress. So, this is 1 over 12. And the integrals here are not too bad. We can actually do the antiderivatives. The antiderivative of 150 is 150t. Integral of 20t, well, 20 and the integral of t would be t squared over 2. So you'll end up with 10 t squared, because we divide the 20 by 2, and then plus 1/3 t cubed. Because add 1 to the exponent, divide by the new exponent. Evaluate from 0 to 12. Now we like evaluating things at 0 because we're going to get 0. When we evaluate things at 12, well, we get 1 over 12, then we get 150 times 12 minus 10 times 12 squared plus 1/3 times 12 cubed. And notice the 12 I can actually divide in. And if I divide in the 12, well, that's going to make things simpler. So I'll get 12 to the 1. This will be 12 squared. So what do we have? Well, we get 150 minus 10 times 12. Well, that's 120. Plus, and I'm going to be a little bit careful here. I have a 1/3 times 12 times 12. Now, 1/3 times 12 is 4, times another 12 is 48. So this part here is 48. So, if we're a little careful, and don't have to be super careful, 150 subtract 120 is 30, plus 48 more means 78. And that's the answer. All right, good. 78 students. Now, of course, I will say this problem was written in a slightly different time when we had people coming to lecture instead of necessarily sometimes watching videos. But we do see the same thing. Oh, not as many people are watching the videos. They're good videos. You should watch them and you should practice. And the more you practice, the more you'll learn. And of course, we love it when the students learn. we do put in a lot of love into our videos. So keep watching, keep learning, and all the way to the end. All right, number 5. So we're given this really bizarre function, capital F of x, which is the integral from 2x squared to x cubed of the square root of 2 plus the cubed root of t dt. And we're asked to find the tangent line to capital F of x at x equals 2. Now, before we begin, it is technically, I think, possible to actually integrate this. You would never ever want to do it. It would be really, really hard, and you would be very miserable, and you would look at your teachers and say, "Why are you doing this to us? I thought you loved us." And we do love you. But our goal in making it look complicated is to give you the idea of saying, hey, that looks complicated. Maybe I should try to do something else. And that's our goal. We want you to see, hey, I've got these really cool tools going on right now. Let me use my cool, awesome tools. All right, so what are our cool, awesome tools? Well, first off, let's think about what you need to find a tangent line to f of x at x equals 2. In general, what would it be? It'd be y equals whatever the function is at 2 plus f prime of 2 times x minus 2. So that's just the generic formula for a tangent line. So I need to find capital F of 2 and capital F prime at 2. Let's start with capital F of 2. So capital F of 2 would be equal to integral 2 times 2 squared is 8. 2 cubed, 8. Square root 2 plus cubed root of t dt. All right, so what's the integral from 8 to 8 of the square root of 2 plus the cubed root of t? Do you know it? Aha! See, we don't have to find an antiderivative because notice the bounds. The bounds match, so this integral is 0. Nice. Good. Good. That makes our life better. All right. Now we have to find the derivative. And now we're like, oh, cool. We know how to take derivatives. And in particular, there's that fundamental theorem that says, hey, taking derivatives of integrals is pretty easy. So let's recall what our fundamental theorem says. The really beefed up version says that the derivative from the integral, say, to g of x to h of x of f of t dt is f of h of x times the derivative h prime of x minus f of g of x times the derivative g prime of x. So this is a combination of several ideas, the fundamental theorem of calculus, plus the chain rule, plus the fact that we can play with the bounds. So what does that tell us? Well, it tells us that capital F prime of x, well, that says take the derivative of f of x. So we're taking the derivative of integral 2x squared to x cubed square root of 2 plus cubed root of t dt is, all right, so let's just identify the f here, little f. That's the inside function. So the rule says take your upper bound function h of x, in our case x cubed, plug it into your original function. So square root of 2 plus cubed root of x cubed. Multiplied by the derivative of the top. So times 3x squared. Subtract. Now take your lower function, the g of x, plug it into your original function. So everywhere where I see a t, I'm replacing it by this new function, square root of 2 plus the cubed root of 2x squared. Then multiply it by the derivative of the downstairs. Derivative of 2x squared is 4x. So that's the generic, what is f prime of x? So what does f prime of 2 equal? Well, that's going to be the square root of 2 plus the cubed root of 2 cubed times 3 times 2 squared. minus the square root of 2 plus the cubed root of 2 times 2 squared times 4 times 2. Well, let's start peeling our onion here. I take 2 cubed, then I take the cubed root of that. That's going to end up being 2. So you can think of it as cubed root of 8 is 2. 2 plus 2, so the inside is 4. Square root of 4, take the square root, you end up with 2. So we have 2 times 3 times 4. So that's going to give us 24. In the second part, again, 2 times 2 squared is 8. Cubed root of 8 is 2. 2 plus 2 is 4. Square root of 4 is 2 times 4 times 2. So that's minus 16, which is 24 minus 16 is 8. So this part is 8. So we put it together and we get that our tangent line is y equals 0 plus 8 times x minus 2, or y equals 8x minus 16. And that's the answer. We're done. Woohoo! We found it. All right. So that's a good principle. If you see something which is suspiciously hard to integrate, don't think, oh, I have to integrate this. Think about, is there another way for me to get around this problem? Okay. Number 6. All right. Find the integral, or rather, antiderivative, because notice there's no bounds here, so that means we're looking for an antiderivative, of sine of root x, sine of 2 root x over root x dx. Now you might think, ooh, maybe I can cancel some root x's, but that's not how it works. So for example, I can't cancel that root x with that root x. That's just not appropriate. It won't work out that way. Now, how can we get things to work? Well, we want to be careful here. Let's think about some things here. I will say before we begin, whenever I see trig functions, I'm always wanted to be in the following situation. I want to compare what's on the inside. Now in this case, I want to compare, and I see, in one of them I see a root x, and the other one I see a 2 root x. Now what that's telling me is that what I'm plugging into the inside of the functions are not exactly the same. So what that means is it's sort of like not when I have different insides, it's like apples and other types of apples. See, they don't mix really well. What you want to do is you want to get the inside of the trig functions should be the same. So we say, okay, well right now they're not the same. So what can we do? Well, we start thinking about all our trig identities that we've learned. And the good news is that even though there are many, many trig identities, there aren't that many that we need in calculus. And we say, well, the biggest difference is that there's a 2. So it's almost like I've doubled my input, or I could say I've doubled my angle. And I'm looking for some identity where I double my angle. Is there any identity like that? Where a doubled angle identity, maybe? Yeah, there is, right? There's actually a pair of them. So the one we won't use, the cosine, is that cosine squared minus sine squared is equal to cosine 2x. Now, sine, that's the one we want because that doubles our angle for sine. So sine of 2x is 2 sine x cosine x. Now that's sine of 2x. So what about sine of 2 square root of x? How does it change this? Well, it just says instead of x, put square root of x. So it'd be sine 2 square root of x is 2 sine square root of x cosine square root of x. So now, if we'll just take a second here, sine square root of x times 2 sine square root of x cosine square root of x all over square root of x dx. So this is already feeling pretty good right now. I'll go ahead and put those signs together. Sine of root x, there's 2 of them, I'll say that's squared. Cosine square root of x over square root of x. So, what can we do next? We've made our insides of our sine functions the same. That makes us happy. But what comes next? Well, at this point, our next step should be, let's look for probably a way to rewrite. We've already used our trig identities to get things to be the same. There's not really an obvious trig identity that says, hey, you should go in this direction. So what are our tools? Our tools are algebra, trig identities, and substitution. These are sort of like the triumvirate, if you will. We want to use those three things. Now, there's not an obvious trig identity. There's not an obvious algebra. So now let's start thinking about substitutions. So what's a good substitution that we can make? All right, well, I see there's this square root of x that's on the inside of my functions. So when I see functions on the inside, I think, hey, that should be a substitution. So let's try that. U equals square root of x, or if you like, that's x to 1/2. So what is du? Well, 1/2 x to the minus 1/2 dx. Now the good news of x to minus 1/2, we actually have that. See, that's like you put a square root of x downstairs. So this part, this is our du, almost, right? The problem is the half. Well, see the 2, that's not a half, that's a 2. But now what we'll do is we're going to do something really cool. It's called multiply by 2. It's something I learned when I was really young. So I can replace this dx over square root of x by 2 du. So if we do that, what do we have? Well, there's going to be a 2 already there. We're going to bring another 2 in. So that's 4 sine of u squared cosine of u du. Because remember that 2 du, that's where the 4 is part of that 2 du. Aha! That's looking good. It's looking good. Now, how about this? This integral. Do we know how to integrate that? Well, not really. I mean, not off the top of our heads. It's not one of our basic integrals. There's really about 8 right now integrals that we should be able to do off the top of our heads. So what can we do? Well, we again think about, oh look, I have something squared. Okay, so what's on the inside? Well, the sine is on the inside. What's the derivative of sine? It's cosine. It's like, what? Perfect. So we're going to make our substitution. We've already used u, so we've got to come up with a new symbol. So let's come up with a double u. We'll call it w. Now, of course, you might think, all right, what if we had to do a third substitution? What would we do? Oh, that's easy. We'd use a triple u. And a fourth substitution would use a quadruple u. So you can make as many substitutions as you need. No problem. No problem. So w equals sine of u. dw equals cosine of u du. Aha! Perfect. Nah, really, it's almost like it was meant to be. So, what do we get? After the substitution, this becomes 4. Sine of u squared becomes w squared. And the cosine u du is dw. Now, good news is, that's something we can integrate. The 4, that's a constant. The way you integrate something to a power is you add 1 to the power, so that makes 3, and multiply by the reciprocal. Now, don't forget, because we're doing an indefinite integral, or if you like, finding an antiderivative, you also have to put a plus c. If you forget the plus c, you'll lose points. And you don't want to lose any points. You want to get all the points. Now, are we done? Well, we're done in the sense of we found the antiderivative, but not done in the sense that we found the answer. Now, the reason we're not done in terms of finding the answer is we started with something that involves x. We've got to end with something that involves x. But this is now where you sort of trace your steps back. You say, well, what was w? Well, w was sine. Okay, so we get 4/3 and replace w by what it is, sine of u cubed plus c. And now we're like, okay, are we done? No, because we're back from w back to u. So we got to go one step back still. I say, well, what was u? Well, it was back here. U was square root of x. So we're going to get 4/3 times sine of square root of x cubed plus c. And now we're really done. We have gotten our function we wanted back with the variable we started with, and life is good. Life is wonderful. All right, that's number 6. Number 7. Oh, this one is fun. If you're staying with friends and you're like, aha, I think I can stump you. Here's a calculus problem. How hard could it be? Even if they know calculus. In fact, the more calculus they know, the harder it's going to be for them. And you're probably thinking, whoa, that means the less calculus I know makes it easier, right? So I can give it to my little nieces and nephews. Well, you got to know some calculus. You got to know some. But I will tell you that the way that it feels like you should do this problem is about the worst way possible to do this problem. So what's the best way? Let's talk about the best way to do this problem. Okay, so we're after some definite integrals. So the answer at the end of this is going to be a number. All right, so we're looking for the integral from 0 to 2, t to the 4th plus 9, and integral 3 to 5, the 4th root of t squared minus 9. So when we don't know what to do, and we don't have very many tools, one way to think of it is sort of say, let's try to get an idea of the picture here. So if we were thinking about this as a picture, I could say, well, let's think here. So suppose I can think of this as going from 0 to 2. So let's say here's 0, and here's 2. And we're going to take the square root of t to the 4th plus 9. Now, this is not a circle, by the way. Let's be careful here, because you might say, aha, it's another circle problem. Wah! No. No circles are going to be harmed in the solving of this problem. The reason it's not a circle is it would have to be square root of 9 minus something squared. Well, that's not what we have. All right, so, well, what do we have? What are we at 0? Well, at 0, plug in, we get 0 plus 9. So that's 3. How about at 2, what are we at? 2 to the 4th would be 16 plus 9 would be 5. 25, right? Square root of 25 is 5. So 3, 5. I can see my picture is already a little bit off. So I start here at 0, 3, and it looks like I end here at 2, 5. And then I go up in some way. So what I have is I have that this curve, this region, that's the integral 0 to 2 of the square root of t to the 4th plus 9. Now, here's sort of your pause and say, there's something suspicious here. Something highly suspicious. 3 and 5. Well, that's 3 and 5 there. Huh? Now let's think about this. Suppose for a second I said y equals the square root of x to the 4th plus 9. So I can think of that as being this curve here, where I express y as a function of x, all right? What if we were to sort of flip? Because we can integrate either with respect to x, or we can integrate with respect to y. Let's try to solve for x. Or we could say y squared equals x to the 4th plus 9. I could subtract 9, and I could say x to the 4th is y squared minus 9, right? Or I could say x is the 4th root of y squared minus 9. That's that function. Oh, okay, so what does that tell us? Well, what it tells us is if we think about what's this piece here, that piece is the same as the integral from 3 to 5 of the 4th root of t squared minus 9. And they exactly match up. So in other words, the bound, we're thinking of it as the upper bound for the first integral, is the right bound for the second integral, where we just sort of interchange integrating with respect to x or y. So they fit together perfectly. Now remember, these are geometrical things. These are areas. I don't know the area of the first piece. I don't know the area of the second piece. But when I put them together, I get a shape. What shape do I get? It's a 2 by 5 rectangle. And the area in a 2 by 5 rectangle is 10. And that's the answer. Wow. This is really fun because it's one of those questions that when you see the answer, you have to think about it for a second. You're like, yeah, it does work. And it doesn't involve any sophisticated tools. It's just a matter of recognizing, let me think about how things can fit together and think about the geometry. So this is a fun one to go back and share with your friends and family. Well, especially if they love doing integration. But if you have friends and family, well, a family, you always have to love. But if your friends don't love integration, you need better friends. All right. Okay, all right. I used to think I could love anybody, but then I discovered, well, I think I need to love somebody who can at least do algebra. And it was true. The good news is my wife, she has a minor in mathematics, so it's like, okay, good, I can love my wife. Whew, good, crisis averted. Okay, number 8. Find the integral. Again, this is an antiderivative of the square root of 1 plus square root of x dx. No little subtle, let's look for pieces of area that fit together, because it's an indefinite integral. When it's an indefinite integral, there's nothing about areas. So we have to think of something else. Now, the first thing you always ask, is this on my list of things I can integrate? And the answer is no, it's not. Your list is very small. So it's like, well, okay, it's not on my list of things I can integrate. So the next thing to think about, is there any nice, algebra? Well, it is not true that you can do square root of 1 plus square root of x. This is false. This is bad. Because look, yes, I know that this would make things easier, but you have to apply things which are true. We're not, in math, our goal isn't to make things, easier for the sake of being easy. Our goal is to make things easier, but still find the correct answer. So we want to avoid false things. So there's not really a good algebra thing yet. So let's turn to our most powerful ally when it comes to finding antiderivatives. And that is the notion of our substitutions. So what's a good substitution to make here? Well, I have a square root function on the outside, so let's make our substitution be the inside part. So we're going to let u equal 1 plus square root of x dx. I got ahead of myself. I'm thinking of the next step. Just 1 plus square root of x. du, derivative of u. Well, this is really x to the half, so 1/2 x to minus 1/2 dx. And at this stage, for those who are uninitiated to the beauty that is substitution, you might say, you must surrender and give up, because it's not going to work. There is no x to the minus 1/2 available. But we are unfazed. So we say, okay, well, what can we do? So let's solve for dx. I could solve for dx, and that's easy enough to do. The half comes across as a 2. X to the minus 1/2 comes across as x to the positive 1/2 du. Now, whenever we do a substitution, our goal is always, 100% of the time, everything has to change to the new variable. So the square root of 1 plus square root of x, well, that's easy enough to change. That's really square root of u. The dx, I can say, well, that's 2x to 1/2 du. But the problem is I can't leave that x to the half in there. So I have this sort of gap. What can I do with x to the half? I need to find a way to replace that in terms of u. So we say, well, what is the relationship between x to the 1/2 and u? And is there one? Well, there is one. You see, u is 1 plus the square root of x. And therefore, if we solve for square root of x, we can say that x to the 1/2 is u minus 1. Right? So u minus 1 equals square root of x, which is x to 1/2. Okay, notice we've succeeded and everything is now a u. So that's good. Have we succeeded in that we've made things easier? Well, certainly there's no more pluses in the square roots. That's good. But can we integrate this? Not yet, but it certainly feels closer to something we can integrate. Let's distribute. Now here's some good algebra. We can expand when there's no square root attached here. So now we can pull it apart. So this is the integral. If I take square root of u times u to the 1/2, that would become u to the 3/2. And then square root of u times 1 is square root of u. But when we're doing calculus, we oftentimes replace square root of u by u to the 1/2. And now we're like, perfect, perfect. See, these pieces are both, there's a technical term for this, nice. And so, since they're both nice, we can find their antiderivatives. All right, so 2, we're going to add 1 to 3/2. That would give us 5/2, multiplying front by the reciprocal. Then minus 2, add 1 to 1/2, that's 3/2, multiply in front by the reciprocal. And because it's an indefinite integral, don't forget you need that plus c. So we end up with 4/5 u to the 5/2 minus 4/3 u to the 3/2. Now, are we done? And why not? Well, no, because other than the fact that our 3 looks very weird, this is u. Where do we need to end up? We need to end up back in terms of x, because we started in terms of x. But now that's when we do our substitution. So we end up with 4/5 times 1 plus square root of x to the 5/2 minus 4/3, 1 plus square root of x to the 3/2 plus c. And that's the answer. Nice. Good. Good. Okay. Number 9. We're given that the integral from 3 to x of g of t dt is the cubed root of x squared minus 1 plus c times x. Find the value of c and the value of g of x. So, well, this is interesting. All right. So there's 2 things we have to find, and we might as well go in the order that's been suggested to us. Now, what does that mean? Well, let's find c. Let's make that process number 1. And g of x, let's make that number 2. So how can we find c? Well, part of our question is, how do we deal with this integral? The integral, we don't know what our function g is, and it could be really messy. And here is where we have our first great aha moment. And that is, pick a nice x. Whoop. Now, you might say, what's a nice x? So, what's a good x to find this integral? So 3 to what number is a really easy integral? In our case, our nice value is 3, because we'd have the integral from 3 to 3 of g of t dt is equal to the cubed root of 3 squared minus 1 plus c times 3. The integral from 3 to 3 is the one integral that's very, very easy to do because the bounds match. Whenever you have matching bounds, that says, hey, the integral, it's automatic. You don't have to do anything at all. Actually, it's a freebie. And so we get that this is 0. 9 minus 1 is 8, cubed root. This will be 2. And of course, c times 3 is 3c. So rearranging, we get 3c is negative 2, or we get c is negative 2/3. All right, so now we know what c is. C is negative 2/3. So let's update what we have. We have the following, namely that the integral from 3 up to x of g of t dt is the cubed root of x squared minus 1 minus 2/3 x. Our next goal is we want to find g of x. If we think about this, we say, you know, this function is related to g of x, and in particular, there's a fancy name for this. This is the cumulative function. Now, this is really almost too fancy for what we're doing, but the important thing to know is that this is really an antiderivative of g of x. So, how does that help us? Well, if I have an antiderivative of g of x, to find g of x, I take the derivative. So the idea is, let's take the derivative of both sides. 3 up to x of g of t dt. And that's going to be the derivative of, and I'm going to go ahead and write this in a more helpful way. X squared minus 1 to the 1/3 minus 2/3 x. So, according to the fundamental theorem of calculus, and remember, that's a fundamental theorem, so it's good to know it. What's the derivative of this integral? It is g of x. All right, on the other side, well, 1/3 comes down. X squared minus 1 to the 1/3 minus 1 is minus 2/3. Anything else? Chain rule, right? Derivative of x squared minus 1 is 2x. And derivative of minus 2/3 x is minus 2/3. So this gives us 2/3 x, x squared minus 1 to the minus 2/3, and then we're going to have minus 2/3. And that is our final answer. Good. I guess we should also box c. So negative 2/3 for c, and there's our function for g of x. Which brings us to number 10. Number 10. We've been doing, this is our 12th quiz. That means 10 problems per quizzes. This is our 120th problem and our last one. I hope it's a good one. I hope it's a good one. Something to remember all the fun by. Find the integral from 0 to 1 of 2x square root of 1 minus x to the 4th dx. Well, how can we proceed? Well, it's not so clear. I mean, if we were to sketch what this function does, it's kind of a strange looking function. What would it do? It starts off at 0 and then goes up and then it's going to come back. It's something like this. It's like I said, it's a very bizarre looking function. It's not so obvious what to do. And there's no geometry to be used at this point with that function. There's no algebra. Again, we can't just break up the square root over that subtraction. Is there a substitution? Now, you might think, okay, well, I could try the whole substitution, say, u equals 1 minus x to the 4th, then du would be minus 4x cubed, but I don't really have an x cubed. I have an x, and the problem is I don't really have a good way to make it into an x cubed without making more square roots, so maybe that's not the right substitution to make. Now, when you're thinking about substitutions, we always think about substitutions, and we oftentimes focus on one place to look for the substitution. So the place that people become fixated on is to say, what's the function on the inside? And I identify my inside function, and off I go. But sometimes the inside function is obfuscated, which is a fancy word which means we have concealed it through algebra or simplification. Yes, Simplification is not always your friend. Simplification can mislead you. The other place to look is to ask yourself, hey, maybe I see a nice derivative. Now looking at this, I say, square root of 1 minus x fourth does not look like the derivative of something I know, but 2x, oh my gosh, or excuse my language, OMG, that's the right way to say it these days. That's something I do recognize. You see, 2x is the derivative of x squared. So if I'm thinking of that as being my derivative, I would say, hey, that would say try x squared as a substitution. So that the derivative of that is 2x dx. See, perfectly matched up. So in other words, we chose our substitution so that we had the derivative in place, ready to go. Now, this is a definite integral, which means that we've got to make sure we update our bounds. You see, the bounds here, these are our old bounds. They're in terms of x. X equals 0 to x equals 1. We're changing our bounds. We're not going to have x bounds anymore. See, the x bounds, 0 to 1, those are the old bounds. We are going to have new bounds, u bounds. These are going to be completely different from what we had before. We are not going to be going from 0 to 1. Instead, we are going to go from 0 to 1. Okay. All right. Now you might say, what did you just do there? All right. Well, what happened, remember, I said these were x equals 0, x equals 1. We oftentimes don't write the x equals, but they are there. They're sort of a hidden part. When 0 squared, it turns out, is 0, and 1 squared turns out is 1. So be careful. Sometimes it looks like we're not changing bounds, but we do always need to update our bounds. The philosophy is whenever you're doing substitution, always update the bounds, always move forward, never move back. The 2x dx becomes our du, and then this becomes the square root of 1 minus u squared. Now before, this original function, 2x squared of 1 minus x fourth, had this really strange shape. How about this function square root of 1 minus u squared? Well, that's not a strange shape at all. Do you recognize it? It's a circle. As I draw my worst circle I've ever drawn. So, that is 1/4 of a circle of radius 1. So, 1/4, the area of a circle of radius 1 is pi times 1 squared. So, 1/4 pi. And that was easy as pi, or rather a fourth of it, but that's the end. What a fun way to finish our set of problems. Of course, we still have reviews and exams coming up, but this was fun. And well, thank you for joining me and hanging out. I know it's kind of an unusual situations you might find yourself in, but I hope that these have been helpful. And we truly want you to succeed, and we hope you have had a great experience. So take care, and hope to see you again. Bye.